Hello, everyone. My name is Rajesh Jayaram, and I'd like to tell you a bit about this recent result we have on estimating the cost of the Euclidean minimum spanning tree in a stream. So this is a joint work with my collaborators, Chen, Vincent Cohen-Addad, Amit, Levi, and Erik Waingarten. So I'll begin with the definition of the Euclidean MST problem. So in Euclidean MST, instead of giving the graph as input, I'm going to give you n points which lie in d-dimensional space. And these points are the vertices of a graph. And the edges of the graph are implicitly defined as the complete graph, where the weight between xi and xj is simply the distance and the underlying Euclidean space. And my goal is to estimate the cost of the MST on this implicitly defined graph, simply given these endpoints as input. So in particular, I'll be focused in this talk on the problem of estimating the cost, not on the problem of producing an approximate MST itself. So I'd like to produce a number r, such that r is an alpha approximation of the true minimum spanning tree cost for some approximation factor alpha. So that will be my goal. It'll become apparent in a moment why I cannot actually hope to output the true MST. So as suggested by the title of this talk, we'll be working in the streaming model. So just a brief primer, the geometric streaming model was introduced in this seminal work of Erik in 2004. And in this model, my data, instead of being given to me all at once, my data set is given to me implicitly through a sequence of insertions and deletions. So at each time step, my algorithm sees either insertion of a point in my data set X or deletion. It's some arbitrary order. And at the end, I have some set which is defined by the points which were inserted but not removed. And I would like to, at the end, output an approximation of the MST of these active points, but I want to use very, very small space. In particular, I want to use very sublinear and n space, where n is the number of points. Instead of storing all the points that were inserted but not deleted, I'd like to use, at most, say, polylogarithmic in n, or a very small polynomial, like n to the 0.1 space. But I will allow polynomial in d space because that's the amount, d is the amount of space required to even store a single vector in d-dimensional space. And note here that to actually produce an MST or an approximate MST, I will need to store order n edges. So I can't hope to do that in sublinear and n space, which is why we can only hope to output an approximation of the cost of the MST. So in what follows, we're going to let capital delta denote the aspect ratio of the problem. So we'll assume that all the distances x between x and y are between 1 and capital delta. And a relatively simple argument demonstrates that if we only want a constant factor approximation or a good approximation to the MST, we can always assume that the aspect ratio is at most order n, where n is the number of points. So for the rest of the talk, it'll help to assume that delta and n are comparable up to a constant. We might as well think of them as being the same. Okay, so what was known for this problem? Well, there was sort of discrepancy with the kinds of bounds that one can get in low dimensional versus high dimensional space. And I'll explain what I mean by that in a moment. So the original paper of Erik in STOC 04 demonstrated that one can get a d times log delta approximation to this problem, where d is the dimension, and very small space, polylogarithmic and n, d, and delta. In particular for L2, where we have dimensionality reduction, I can always reduce the dimension to most log n. So I can think of this as being a log n times log delta approximation. So this is a very good space algorithm, but it uses an approximation which depends on d in general. On the other hand, we can get a very good approximation, for example, a 1 plus epsilon approximation, if we allow the space to depend exponentially on the dimension. For example, if we allow the space to be roughly log delta over epsilon to the d. Now, of course, this is the result of Erik, and Solar, and this is only useful, of course, when the dimension is at most log n. Otherwise, I'm just storing the whole data set, and I've gotten no improvement. Now, on the other hand, for this sort of high dimensional regime, this paper of Andoni, Erik, and Kraufgammer showed that one could get this log n times log delta approximation in any metric, not just Euclidean metric, where dimensionality reduction is possible, and in very small space, the polylog n d. So they showed that even for L1, one can get a very good approximation, log n times log delta approximation in polylog space. And then this was the best result that was known for quite some time. And recently we were able to remove one of these log factors. So if we think of delta as being comparable to n, this is like a log squared n approximation. And we reduced that to a log n times polylog log factors in STOC of last year, also using very good space, log n, polylog n of n and d. So we've gone from log squared to log n approximations, but this is still the best result that was known. And what I want to tell you about today is the first constant approximation for this problem in the stream. In particular, for any epsilon, we obtain a 1 over epsilon squared approximation in space n to the epsilon times polynomial indeed. So we think of epsilon as being a small constant. This is a constant approximation using sublinear space n to the, some small constant. So the space is no longer polylogarithmic. It's slightly worse, but the approximation is 1 over epsilon squared. In theorem format, what this is saying is for any epsilon, this could be a constant or even subconstant. There's an algorithm that produces a 1 over epsilon squared approximation given only one single pass over the stream using space n to the epsilon. Now you could ask whether this is the best one can hope for, or whether we could even get arbitrarily good approximations in a single pass, like say 1 plus delta approximations for a very small delta. We show actually this is not possible. In particular, we show a lower bound for this problem. Any algorithm that makes only a single pass over the data and outputs better than some constant, say better than a 1.1 approximation, actually needs to use the least square root on space. So this demonstrates that if you want an arbitrarily good approximation to the MST, better than a constant, you cannot do that in a single pass over the stream unless you're willing to pay large polynomial square root n space. This also demonstrates that our algorithm and the regime of n to the 1/2 square root n space is giving a tight approximation up to a constant. But despite this fact, we actually show that despite the fact that we cannot get arbitrarily good approximations in a single pass over the stream, we show that if you're allowed multiple passes, we can actually break this lower bound and get arbitrarily good approximations. So all the results on the prior slide were for single passes over the stream. Now, if I allow you any s greater than or equal to 2 passes over the stream, I can actually output an approximation that gets a 1 plus log s over epsilon times s multiplicative approximation to the MST cost, using the same amount of space as before n to the order of epsilon. So in particular, if I think of epsilon as being some small constant, then using roughly for any approximation parameter alpha, using order roughly log alpha over alpha passes over the stream, I can get a 1 plus alpha approximation to the MST. So this shows that the prior lower bound can be beaten with multiple passes over the stream. Okay. So here's a roadmap for what I want to tell you about today. So I first want to talk about how one even goes about trying to first estimate the cost of the minimum spanning tree in a stream. It's not clear what approaches could even be used. And then I'll show how, using some ideas that were implicit in prior work, how one could obtain, with a bit of extra work, a log delta pass algorithm for the problem. And then I'll introduce some of the main ideas in the paper, which should culminate with a 2-pass algorithm. And the techniques used to compress this 2-pass algorithm to a single pass will be slightly outside of the scope of the talk, but many of the main ideas will be implicit already in this 2-pass algorithm. So before we jump to the estimator that we use in our paper, I want to say a word about the techniques used in prior works. And in fact, the technique, because there is one clear technique which underlied all the approaches in prior works, and this was known as the tree embedding technique. So what is a tree embedding technique for streaming algorithms? Well, the idea is to take your points in your high dimensional space, your d-dimensional space, and apply a randomized embedding into a tree metric. The reason one would do this is that once your points are lying in a tree metric, many problems, for example, computing the cost of the minimum spanning tree, can be accomplished very easily in a stream because there's a very easy representation for the cost of an MST inside of a tree metric. So once we're in a tree metric, we can get a good approximation. So the question is, what is the approximation we paid to embed into the tree metric? And the series of works essentially gave better and better approximations by tighter and tighter analysis, culminating in this log n approximation from STOC of last year. Unfortunately, it's known that tree embeddings necessarily must pay log n distortion in this average case embedding, an expectation over the distortion of the embedding. So we can't actually hope to get better than a log n approximation using such tree embeddings, which means that if we want to get a constant approximation, which is the goal of this talk, we need to look elsewhere. So that's precisely what we do. Instead of using tree embeddings, we use a very different kind of technique, which is an estimator based on counting connected components. This is a very nice idea due to this paper of Chazelle, Rubenfeld, and Trevisan. And this paper wasn't studying the streaming model, but they were studying a similar sublinear algorithms model. This is the sublinear query model. So in this model, there's this implicit n by n distance matrix. We can think of these as being the implicit edges in our complete graph. And I can query to get the weight of any edge ij. And I want to output the cost of the MST, making a very small sublinear number of queries. So less than n squared queries in this case. And the results were later improved by Shumai and Solar for the case of metric spaces, where these distances satisfy the triangle inequality. So now let me say what the idea is. So it relies on this very simple but very crucial definition known as a t-threshold graph. So this is simply an auxiliary graph that's defined implicitly. So given a set of points, the t-threshold graph of that set of points, gt, is simply the graph such that 2 points are an edge, xy is an edge, if and only if the distance between those points in the original space is less than t, the threshold t. And now I'm going to just denote c sub t to simply be the number of connected components in this graph. And what we'll see is that if we can simply estimate the c sub t's, the number of connected components, then we'll have a good estimate of the MST. And the reason that this is fairly simple to see. Like if you imagine what a greedy algorithm does, like Kruskal's algorithm for MST, it adds edges greedily to the MST without creating cycles. And every time, if you think of it doing starting with all points in their same connected component and merging them as I add edges, every time I add an edge, I merge 2 connected components. So in particular, the number of edges added with weight between t and 2t is exactly the difference between the number of connected components at level t and the number of connected components at level 2t. So I can simply write out a constant factor approximation for the cost of the MST just by looking at these differences in the number of connected components in the threshold graphs. And after rewriting it, we can see that it's just this sum over all log delta levels, the level itself, 2 to the I, times the number of connected components at a level C of 2 to the I. So if I can just estimate the sum, then I'm in great shape. So here's an idea of how we could estimate it. This is the estimator again, due to Giselle, Rubenfeld, and Trevisan. And I'm going to introduce a bit of notation for a point P and a graph G. We're going to let CC of P, comma G, to be the connected component in the graph G, which contains my point P. So here's the algorithm. I'm going to first sample a point uniformly for my graph, and then I'm going to define x sub t of p to simply be 1 over the size of the connected component in the graph that contains my point. And then I'm just going to output n times x sub t of p. So this is just some random variable. Why is it the right thing to output? Well, we can just compute its expectation. We can do that by summing over all the connected components, and then each component sum over the number of the points that we could have sampled. Each such point would output 1 over the size of the component. So each component is contributing 1 to the expectation of this estimator. Therefore, the expectation of the estimator is the number of components. So great, we have an unbiased estimator. Okay, so let's put that aside. Now let's ask, how could we actually estimate this quantity, this estimator? How could we implement it in a stream? Well, let's assume for simplicity we're in an assertion-only setting, and how could I actually estimate this value? Well, I could allow myself multiple passes over the stream. On the first pass, I could use something like reservoir sampling to sample a uniform point P. Now that I have this point, well, I need to know how big its connected component is in the graph GT. And the only way to do that is, in some sense, to run a breadth-first search. I need to explore the connected component. So on every subsequent pass over the stream, I can make another pass over the stream and find all the points that are within distance t to p. These are the points that are adjacent to p. And so now I mark all those points. And then on the next pass, I could do another step of BFS by marking all the points adjacent to those points. And then on each subsequent pass, I can make one step of the BFS and so on. And so this is how one could explore the connected component. But the issue, of course, is that this connected component could have very large diameter. In particular, the diameter could be polynomial in n. And so doing this process would be very expensive. It would require way too many passes over the stream. And I promised a constant pass algorithm, let alone a polynomial pass algorithm. So, what remains in the talk, this is sort of the crucial issue we'll have to deal with. We're going to see how we reduce the number of passes required to produce an estimate of this value xtp. So the first thing we'll do is we'll show how to do it in log delta passes. And this is a very nice idea that was implicit in prior work, in particular implicit in this paper of Schumann and Solar. They had this very nice observation that in a metric space where I had the triangle inequality and these distances between points, we can actually cut off this breadth-first search after only log delta steps. Remember, delta is the aspect ratio. In particular, you sample your point and you start doing a BFS, and if the diameter is larger than the log delta, then I'm just going to output 0. I'm going to cut off the BFS, and instead of even outputting my random variable, I'll output 0. So in particular, if we define x hat of t of p to be x t of p, if the point p that I sampled lies in a kinetic component with small diameter, that is diameter smaller than some constant times log delta, then I'm in great shape. Then I output that, and I can do log delta passes to compute this. Otherwise, if the diameter is too large, I just stop the BFS and output 0. So I can always do this in log delta passes, but I'm forgetting some of the kinetic components. In particular, I'm not counting the kinetic components that had large diameter. I'm only counting the ones that have small diameter. And in fact, they show that this is not a big issue. They show that even if you do this and you only use this modified estimator that cuts off your log delta passes, I can still get a constant factor approximation to the minimum spanning tree in expectation. So the expected value of this modified random variable is between MST over 2 and 2 MST on summed over all levels. And the intuition for why this is true is that if I have a kinetic component in my graph that has a very large diameter, then it must have a lot of points that are far from each other in some sense. So the cost of this kinetic component, the MST cost, if you just look at the edges that must be inside that component, for levels less than t, with edges like size less than t, that cost must be large. So even though I'm losing a value of t, because I wanted to output t times this value xtp, I'm losing only a very small value compared to the cost that was already inside the MST. So by outputting 0, I've lost very little. In other words, there cannot be very many kinetic components with large diameter. Okay, so given that you believe this lemma, there's a very simple log delta pass algorithm. Sample a point uniformly from my vertex set, and then do log delta steps of the BFS from that point. I can do one step in every pass over the stream. If I recover the whole kinetic component, great, output the value. Otherwise, the diameter is too large, and I can output 0. And by the value, I mean 1 over the size of the kinetic component. And so we just show that the expectation of this random variable is a constant factor approximation. So what is the issue? Well, of course, expectation is not enough. The variance of this estimator is quite large. And that's very easy to see. So for example, you can imagine that my graph GT my threshold graph consisted of a lot of points that are very close to each other. Let's say n points that are all in a clique, plus log n vertices that are isolated. They are their own kinetic component. Well, if I want to get a constant factor approximation to the number of kinetic components, I better sample some of these isolated vertices, because I have each of them is their own kinetic component, and I have almost all my points in the single kinetic component in the middle. But to even sample a single isolated vertex, I need, roughly n samples. And each sample is contributing to my space. So I wouldn't be able to do this in sublinear space. So somehow we need to deal with the variance. So the way we do that is by an idea that's not particularly new, but we use it in somewhat of a novel way. So we apply a simple quadtree discretization, a random hypercube discretization over the d-dimensional space. So we impose a randomly shifted grid of hypercubes where the side length of each hypercube is t, that's the current threshold that we're working with for the graph GT, divided by some large polynomial in D. And then we look at these blue points, which are the centroids of the hypercubes, and we map each orange point, the points in the data set, to the centroid of the hypercube which contains them. And now this gives us a new set of points. We've discretized all the points, possibly mapping multiple points to the same centroid. And the first fact is that by changing our vertex set from the orange points to the centroids, if we look at the threshold graph of these centroids, we actually have preserved the number of kinetic components approximately. We haven't distorted the threshold graph by very much. And the reason is because we've only moved each point a very small amount, t over poly d, when compared to the threshold t. The last key point is that this fact which was used throughout the paper, and it's the fact that you can actually relate the cost of the minimum spanning tree in expectation to the number of centroids, the number of discretized points. So in particular, the MST cost is at least t over poly d times the number of points, discretized points that you get after this process. This is important because this allows us to bound the variance of our algorithm by something depending on the number of points that we're sampling from, which therefore depends on the MST cost. So in particular, if we just run our algorithm on v hat of t, which is the set of discretized points, then the number of discretized points is now bounded by some factor of poly d over t. So t times the number of discretized points times our estimator has bounded variance in terms of the MST. So we can, with poly d samples, get a good approximation. So just at a high level, using this approach, we can get a log delta pass algorithm with a constant approximation using a very small amount of space, poly d times log delta. And in fact, there's no epsilon here, you'll notice. So this algorithm is polylogarithmic space in n. But now let's talk about how to improve this algorithm. So how could we go from log delta passes, compress that algorithm to a 2-pass algorithm? So here's one key but simple idea. So imagine that I'm going to allow 2 passes. On the first pass, what I can do is I can sample my point P uniformly from the set of all vertices. Now remember, I'm working only with the discretized points. I've forgotten about my original point set. I've applied this random hypercube. I've mapped all them to centroids, and I'm only working with the discretized points. So now that I've done this, I know that if I could just do log delta steps of my BFS from this point P, I'd be in great shape. So let me try to do them all at once. How could I do that? Let me look at this point, and let me try to store on my second pass over the stream all the points which land on the metric ball, P, centered at P, at distance at most T times log delta away from that point. And notice that every point that I could possibly explore in a log delta step BFS from my point P would be contained in this ball. Well, why is that? Well, it's simply the triangle inequality. Each point that I could explore moves me distance T away from the last point I was at. So log delta steps of a BFS moves me distance at most T times log delta away. So I just store all the points in this ball. And then when I have them afterwards, at the end of the stream, I could run the BFS locally in memory because I have all the points that I could possibly need to explore on the BFS. So this would allow me to run log delta steps of the BFS and be in great shape. What's the challenge? The challenge is this metric ball could be very large. In fact, it could have almost all the points in it. And many of the points, for example, these blue points here, need not be in the same connected component as the point that I'm trying to explore from, because I'm looking at a very large ball compared to the threshold. And I'm only allowed to use space n to the epsilon. So if this ball has more than n to the epsilon points in it, then I simply cannot store it. So we're out of luck in this case. If it was small, we could run the whole BFS, but in general, we cannot. Okay, so let's try to weaken what we want a little bit. Instead of storing a log delta size ball, let's just try to store the biggest metric ball that we can, subject to our space requirements. So in the first pass, we do the same thing, sample a point uniformly. And on the second pass, I'm going to store the largest metric ball centered at P with radius alpha times T. So this alpha is a parameter. I'm going to make alpha as big as possible such that the ball has less than delta to the epsilon points. So here I switch delta to n to delta. We're thinking of these things as being the same value for simplicity. And I can, of course, store this ball because the space isn't too bad. And now, for thinking of alpha as an integer, I can run alpha steps of the BFS. Why? Because I've stored the ball with radius alpha times t around my point. Now, the issue now is that, as we've seen, it may not always be possible for alpha to be log delta. Alpha, in some cases, maybe I could only store the ball that would allow me to make 2 steps of a BFS. So the question is, what do we actually output? What is the estimator? A simple idea would be just output 0 whenever I cannot explore the full kinetic component in these alpha steps. But it's very easy to see that if I output 0 for shorter BFS, for example, for a BFS any smaller than log delta, then there's an example where almost all the weight of the estimator is contained in connected components that have diameter some constant times log delta. So in this case, you would actually output 0 as your whole estimate. So if I were to output 0 in this case, I could have an instance where my entire output was 0, and clearly I've gotten no good approximation here. So the key idea is we need to develop now a new estimator, which gives some approximation, provably, even when the breadth first search is shorter than log delta steps. The approximation can be larger, but it needs to give some approximation. And that's what we'll do now. So what we now show is an estimator for shorter breadth first search. So given a point P and some alpha integer alpha, I'm going to define this set ST, alpha of P, just be the set of vertices that would be explored if I did alpha steps of a breadth first search starting from the point P in the graph GT, the threshold graph. In other words, These are just all the points that are at graph distance and most alpha hops for my point P. And then I define x hat of T alpha P to just be 1 over the size of the set. And I'm just going to output this value. So in other words, I just do alpha steps of the BFS. I look at all the points that I saw, and I output 1 over that. Notice that because this is a subset of all the points I would explore in the entire kinetic component, I'm outputting 1 over that set. This means that my estimate is always going to be an overestimate because I wanted to actually estimate 1 over the size of the kinetic component. Instead, I'm outputting 1 over the size of a subset of the kinetic component. So this is always an overestimate. But actually, we're able to show in one of the key results of the paper that you get some approximation from using this overestimate. In particular, for any alpha, even alpha equals 1. So even if I can only make one step of a BFS, the expectation of this new estimator is correct is equal to T times CT up to some additive error, which is 1 over alpha times the cost of the MST. So you can see that if I made log alpha equals log delta, then my additive error would be MST over log delta. And I'm running this for log delta level, so I'd get a constant approximation. So this actually shows that even this modified estimator would also work if I could always run log delta steps. But the key takeaway, even more so, is that even if I only do alpha steps of the BFS, even alpha equals 1, say, then I still get an approximation of the MS to the value that I'm trying to estimate at that level, which is T times the number of kinetic components at level T. So in particular, for alpha equals 1, I get an additive MST cost to that level. So I can't do this for every level, of course, because if I did this for every level, with alpha equals 1, then I would get an MST additive error every level, and I would get a total of log delta times MST additive error because there's log delta levels. So even though we have this nice lemma that shows that shorter BFSs give some approximation, we can't always run a shorter BFS because we get this additive error whenever we do. And so the last key thing that we put together is we show that this can't happen too often, this case where I cannot run a large BFS. In particular, we showed that most of the time, I can do a long enough BFS such that globally the total estimate produced by my estimator over all levels and all points is a constant factor approximation. Specifically, we show that for every point P in the graph GT and for every level T, if I store the biggest metric ball BP alpha times T that's possible within our space bounds of n to the epsilon, after sampling that point P, then the total error of my estimator in expectation over the sampling and output estimation process is at most 1 over epsilon times the MST. So this is the key result of the paper. We show that for every point, you store the biggest ball that you can up to your space, output 1 over the number of points that you found in that kinetic component after exploring it, and you get a constant approximation. So I don't have time to really go into the proof of this. There's a good detailed explanation in the overview of the paper. But just to sort of summarize and wrap up the approach of this paper, our main, 3-part approach is that we know that if I can do log delta steps of the BFS from every point, then I can get a good approximation. This was known from prior works. But of course, I can actually simulate alpha steps of a BFS for any alpha in a geometric graph in one of these threshold graphs. I can do that in one pass if I just store all the points in this metric ball of radius alpha times T around the point that I'm doing my BFS from. That's just triangle inequality. So if I can store this ball of radius alpha times T, I can do alpha steps of the BFS. Now, our next observation was that for any alpha, even if I only run alpha steps of the BFS, I still get some approximation to the MST. And lastly, we show that if for every point in the space and for every level, I store the biggest alpha that I can, the largest metric ball that I can, output what I can estimate from that ball, then I get a constant factor approximation. And that's the main takeaway. I want to end briefly with a couple of open problems. So there's a variety of very tantalizing open problems in this area of geometric sketching and streaming, and partially that's due to the fact that we have really a lack of techniques to prove lower bounds, I would say, in this area. In particular, there tends to be a very large discrepancy between the space complexity of the upper and lower bounds for various problems in this model. So in particular, in this paper, we actually did prove a lower bound. We showed that any algorithm that gets better than some constant, a 1.1 approximation, needs polynomial space, square root n space. But the natural question is, well, what if I ask for 100 approximation? Well, our techniques don't allow us to say anything about this. Like, if I allow the algorithm to make a single pass and get a large constant approximation, for example, this is the type of guarantee given by our algorithm, can we prove any lower bound? In particular, can we prove something like the following? for any epsilon, we can get an n to the epsilon space lower bound on an algorithm with using one pass over the stream that achieves some approximation depending on epsilon, say 1/epsilon approximation. There's a number of problems for which this would be very nice to prove this for, not just MST, but also related problems like estimating the Earth mover distance in the stream, or facility location, or approximate the diameter. For the three of these problems, MST, facility location, diameter, we actually have bounds that look exactly like this, n to the epsilon 1/epsilon, or 1/epsilon squared approximation. And these are very closely related to the trade-offs, the optimal known trade-offs for nearest neighbor search, like n to the epsilon runtime / space, extra space for a 1/epsilon approximation. And these do show up quite a lot as part of where our approximations are coming from. So whether we can prove better lower bounds here would really be saying something strong about how nearest neighbor search can be done in the stream. We're connecting these problems to nearest neighbor search. Lastly, I want to talk about one of those problems that I mentioned on the last slide, and that's this Earth mover distance problem. So if you haven't heard of it, it's a classic problem. Instead of giving one set of points in d-dimensional space, I'm going to give you two sets of points, A and B. And my goal is to approximate the Earth mover distance between these two sets. What is that? Well, that's the minimum over all possible perfect matchings from the points in A to the points in B. And then for that matching, the cost is the sum over all the A points, the distance between A and the point it was matched to in B. So this is a bipartite metric maximum matching problem. Now, it turns out that a lot of the techniques that were used in prior works that we saw before carry over directly to Earth mover distance. And that's because, recall, these papers were using tree embeddings, which is a very generic approach. Once you go into the tree, almost all problems in the tree can be solved very efficiently. So we actually got a log n, we knew about a log n log delta approximation from this paper. And via our prior STOC paper, we knew about a tilde of log n approximation using polylog n d space. But an open question is, can we get bounds comparable to the bounds obtained in this work, but for Earth mover distance? In other words, can we get something that's like a 1/epsilon approximation, or even a 1/epsilon squared approximation, using space roughly n to the epsilon for the Earth mover distance problem? Basically getting matching bounds for this problem. That would be very nice. And of course, the techniques that I presented today are very specific to MST. So we would need to develop a number of techniques which are, again, specific to EMD. And part of this comes from the fact that we're moving beyond generic techniques like tree embeddings. We're looking at problem-specific structure. So that would probably be needed for this approach. So that's all I had time to talk about. Thank you so much for your time.